Good day, everybody. My name is JV Galan, and together with my group mates Andrea Alvarez, Zairel Kaadan, and Nawi Mendoza, we present to you examining the principles and significance of hemodynamics on physiological flow and coronary stenosis using a simplified vascular model. Without further ado, let us start.
Fluid mechanics studies the behavior of liquids and gases as well as the forces that are involved when they are at rest or in motion. Its study can be applied to a wide range of fields, including but not limited to chemical engineering, mechanical engineering, and biological systems. The five most useful relationships under fluid mechanics include kinematic relationships, which study on fluid properties, stress relationships for flow properties, conservation relationships for physical properties, regulating relationships for geometric properties, and constitutive relationships, which study on laws to describe the flow of fluid through mathematical descriptions and models. One of the concepts under the study of fluids include hematology and rheology, which study on the nature, function, and flow of the blood. The blood is an important human body fluid that brings nutrients to the cell and carries harmful metabolic waste away from them. Its components include plasma, erythrocytes, leukocytes, and thrombocytes. The circulatory system works by the blood being pumped by the heart and being circulated all over the body through arteries and veins. Blood is circulated through a series of contractions with the use of the independent chambers of the human heart called atria and ventricles. Due to the heart's pumping action, blood can enter the arteries through spurts or pulses. As the blood flows through the different blood vessels around the body, the blood pressure changes as a result of losses due to arterial walls expansion and contraction and viscous friction. With the person's actions, such as during abrupt movements or after a long time of sitting or standing, the flow of blood also slightly differs. Aside from temporary and sudden movement, heart diseases also cause changes in the blood pressure of a person. One such example is arteriosclerosis. It is when the arterial wall thickens and the artery narrows due to the accumulation of plaque deposits. It is one of the most common heart diseases, and it greatly impairs the function of the circulatory system. Due to this blockage, the blood flow is also affected. Blood flow can be investigated and further studied upon through Bernoulli's equation and viscosity and Puisel's law. Puisel's law represents laminar flow such as blood flow in blood vessels. Laminar flow is when the velocity is highest at the center of the pipe or vessel and decreases towards the walls, wherein at the walls of the vessel, the fluid is stationary. If viscosity is taken into account, the Puisel's law is followed. On the other hand, if frictional losses are not taken into account, the flow is governed by Bernoulli's equation. It gives the relationship between pressure, velocity, and elevation of flow. It involves the law of energy conservation since without friction, the sum of the values will remain constant no matter the flow. For the objectives, this study aims to make a mechanical model of the blood flow in blood vessels. Specifically, it aims to first, to propose a mechanical model of horizontal blood vessel emphasizing the applications of Puisel's and Bernoulli's equations. Second, to study how the pressure differences in the vessel, radius of a vessel, viscosity of the blood, and length of a vessel affect blood flow. Third, to imitate the stenosis brought about by arteriosclerosis on the mechanical model. And lastly, to investigate the effects of arteriosclerosis on the blood pressure in the constricted region.
The experimental setup consists of two independent lines sharing a common flow control valve. The upper designed to investigate Bernoulli's equation where frictional forces are ignored, and the lower for Poissier's law. Incompressible Newtonian fluid is assumed to flow through this system. Elasticity of the vessels is not considered, and laminar flow is observed. A rotameter measures the flow rate at the upper pipeline, which has an inner diameter of 4 millimeters. The middle section of the pipe is detachable and functions as a mock stenotic artery, where a narrowing of the diameter to 2, 1.6, 1.2, and 0.8 millimeters is individually tested. Two small T-junctions with its ends at the center of the middle and first section of the pipe allow for the measurement of a pressure drop using a differential low-pressure transducer, which outputs a signal that can be measured using a millivoltmeter. The bottom pipeline uses a mini turbine flow meter, which is recommended for viscous fluids and thus suitable for validating Poissier's law. It outputs a frequency signal that is picked up by an oscilloscope. The length of the pipe is 160 centimeters with a diameter of 4 millimeters. The pressure drop is also measured using a differential transducer, But here the T-junctions are soldered at both ends of the pipe.
Moving on to the expected results, in investigating the flow of blood in the blood vessel through Poissier's law, the lower pipeline system of the mechanical model will be used and observed. For this experiment, the fluid must first exhibit laminar flow and must be a viscous incompressible fluid in order to apply Poissier's law. If the conditions are met, then the flow rate of a fluid can be calculated using Poissier's equation. From the theoretical data, the flow rate is expected to increase when the pressure difference or the radius increases, and it should decrease when the pressure difference or the radius decreases. On the other hand, the flow rate is expected to decrease when the viscosity or the length increases, and it should increase when the viscosity or the length decreases. According to Chaudhry et al., blood flow is measured by the change in pressure divided by the resistance of the flow. Since blood flow is laminar and blood can be modeled as a viscous incompressible fluid, applying Poissier's law to the blood flow equation will yield the flow resistance equation, which denotes that radius, viscosity, and length are the factors that affect blood flow. Similar with the theoretical data obtained using the mechanical model, increasing the diameter as shown during vasodilation results in a lower resistance, thus an increase in blood flow, and decreasing the diameter as shown during vasoconstriction results in a higher resistance, thus a decrease in blood flow. For the viscosity and length, an inverse relationship with flow rate was observed, similar with the obtained theoretical data. Since blood is a mixture of fluids and particles, increasing either of it will increase the viscosity, resulting in a higher resistance, thus a decrease in blood flow. This is why any conditions affecting erythropoiesis and liver abnormalities can decrease blood flow. Moreover, since viscosity is temperature dependent, this relationship also explains why less blood flow is observed through cold feet and hands. For the length, additional meter of vessels from gained adipose tissue will result to a higher resistance. Thus, the stress to the heart increases as the heart needs to overcome greater resistance to maintain normal blood flow.
In the figure shown in the slide, it is evident that the shape is changing. At one end, the fluid flows at a speed u1 and the area at that side is labeled a1, while u2 and a2 are the outlet flow speed and area, respectively. This relationship can be demonstrated by the equation of continuity as we can see here on the slide. Now, in the body, if an artery becomes more narrow, the speed of the blood flow increases. This is because the mass flow has to be conserved, so if the tube becomes more narrow, the flow rate has to increase. This constriction usually occurs in those with arteriosclerosis, where plaque builds up in the arteries, thereby constructing blood flow. In addition, Bernoulli's principle states that as the velocity of the fluid increases, the pressure decreases, which we can see in this equation. Ignoring gravity and assuming steady-state flow, the equation for the pressure in a blood vessel with a stenosis can be obtained by combining Bernoulli's equation and the equation of continuity, as we can see here. Since A1 is greater than A2, the last term of the equation will be negative, leading to a decrease in pressure at the point where stenosis occurs, where P2 is less than P1. Mass flow conservation will also show that velocity is higher at the stenosis. Using the mechanical model, the effect of reducing the diameter of the pipe on velocity of the outlet flow is shown here. Here we have the values of A1 and we have the value for Q, and we also have its formula given as UA. Now to get the value for the inlet flow, which is known as U sub 1, we have to divide Q by A. And here we have the value, which is 0.66 meters per second. Now that the value of U sub 1 is obtained, it is now possible to solve for U sub 2 using the equation of continuity. And the value for that is 2.64 meters per second. Now the sample computation to calculate for the change in pressure in the constricted artery is shown here. We have the values for A1 and A2, and we also have the value for U1. Therefore, we can calculate for the value of P2 minus P1 or delta P, which is the change in pressure. And here we have a value of negative 3.267 pascals, which indicates a decrease in pressure. These calculations quantitatively validate Bernoulli's equation in explaining the impact of stenosis on flow rate and local pressure within the vessel. Given these theoretical values, an increase in the velocity of the fluid at one point in the segment is associated with a reduction in diameter. And that has been our presentation on an experiment design. We thank you for your time, and we hope that you've learned something from our presentation. Thank you.